Hello and welcome to this unfortunately virtual presentation. So my name is Paolo. I'm a PhD student at the University of Notre Dame in Indiana. And today I'm going to talk about the work that I have been doing in the last year or so. So my research usually deals with atmospheric modeling, so numerical simulations of various atmospheric processes. Today, I'm going to focus on an application of the tools that we have as atmospheric modelers to the energy community, to the wind energy community in this specific case. And I entitled this presentation a modeling framework based on multi-scale atmospheric simulations for wind energy assessment. And I kept it pretty general deliberately, although I'm mostly going to focus on one specific case study that basically motivated the development of this modeling framework. The case study is the one of Saudi Arabia. And let me start by motivating this. Like, why are we interested in wind energy in Saudi Arabia? As you can imagine, the total installed capacity of Saudi Arabia is pretty much dominated by fossil fuels, right? They have 60 gigawatts of installed capacity, and virtually all of it is dominated by fossil fuels. However, in 2016, Saudi Arabia started to set some targets for renewable capacity, and a big share of this is definitely solar power related, because they have, of course, a lot of potential there. But at the same time, they had a very interesting share of wind energy too. So in 2016, they claimed that they wanted to install 9 gigawatts by 2032. Right now, they revised this claim upwardly, and actually now it's 16 gigawatts. So they changed this number a couple of times, but the latest figures are saying that they want to install 16 gigawatts of wind by 2032. Just to give you an idea on how big this 16 gigawatts is, if you look at the ranking of wind power installed capacity in 2017, for example, well, 16 gigawatts would be the 7th largest country in the world by wind power installed capacity. So that says something about the commitment, right, that the Saudi Arabia's government basically is willing to take. That's where we come in, right? So now it's 2020, so 4 years have passed since 2016, and actually only one project, one wind farm project has been tendered in the last 4 years, and it's a 400 megawatts project. So out of the 16 gigawatts that they're planning to install, only 400 megawatts are actually installed or are actually planned to install by now. And so KAUST, which is the King Abdullah University of Science and Technology in Saudi Arabia, they have sponsored 2 grants to accelerate the deployment of the wind energy infrastructure. And what I'm going to talk from now on basically is some of the story that we have done so far. One of the main barriers to the development of the wind energy infrastructure in Saudi Arabia and in other actually emerging countries is the lack of accurate data, right? We need actionable recommendations on where to build wind farms, first of all, but also which kind of models are more suitable to some sort of wind regimes, or I don't know, how tall the turbines should be built, or how much should they cost, or something like that, right? So we have some previous studies in Saudi Arabia. There are some few observations, so a few monitoring sites that measure wind speed across Saudi Arabia, but it's definitely not enough to reconstruct the whole map. We have some studies that relied on climate models output. We have some studies that relied on coarser analysis data, but there is still the need of more and more accurate data to actually have this kind of actionable recommendations that the government eventually can take as very valuable information to plan the wind energy infrastructure. So we've developed this modeling framework that I'm summarizing here, and the main part of the whole framework is the box that I'm calling wind data. So first of all, in all these kind of studies that are related to wind power potential, you need to know the wind, right? The wind patterns, the wind flows around the country. And again, it's not a simple task because you cannot really rely on observations only because you don't have enough. Climate models or reanalysis are usually too coarse. So most of the times you have to develop your own, basically your own simulations of wind speed across the country. And then of course you can validate those with the observational data that you have. And instead of just, so one approach would be just, okay, let's try at least to quantify the wind across the country and find the areas in which the wind speed on average is the largest and suggest those as area in which we should build wind farm. Instead of just limiting ourselves to this step, we decided, and that's basically the main novelty of this, of our modeling framework, and I hope you will appreciate this in the rest of the talk, is that we actually integrated a lot of other more engineering or practical considerations into the picture. So it's not only about wind speed, we took into account detailed cost data. So something like, okay, turbine specific installation cost, O&M, but also if you're building, for example, a wind farm very far away from the existing electricity grid, you would need to build the electricity grid from the wind farm to the existing grid to actually connect it, right? And that entails a big cost. So we kind of quantified, or at least provided a methodology to quantify also all these costs. And we took into account geographical constraints as well. So you cannot build a turbine in urban areas, in wildlife reserves, in rough terrain as well. So we set, basically, we're just giving us some procedures to identify, like, what do you mean by rough terrain? How can you not, like, how rough should it be for being unsuitable for wind turbines? Or what do you mean by urban areas? Like, those kind of practical considerations. And we kind of built a protocol on how to identify all these geographical constraints as well. So the idea is to take into account, I mean, there is much more than this, and now I'm simplifying this. If you want more details, there's actually a paper published about all this framework. But basically, we are combining a lot of data coming from different sources, so wind data, cost data, geographical data, and so on. And the very output of all the procedure is what we call optimal siting. So basically, we can select the areas in which is most cost efficient to build or harvest wind energy. And we can also say something about, I don't know, how tall should be a turbine, which model is more suitable for that specific region. How large should be the turbine? It should be a 2 megawatt turbine, a 3.5 megawatt turbine, and something like that. This is the general, say, theoretical framework in which we acted. So the first step, and that's the step in which we have the most tools as atmospheric scientists, is to provide the wind data. So we ran some simulations. We actually ran two different kinds of simulation, mesoscale, and that's what I'm going to mostly focus on here, and microscale simulations as well. And we used the code that is called WRF. Probably some of you actually have heard about WRF. So it's basically solving Navier-Stokes equations, usually Reynolds average Navier-Stokes equations. So you're providing a domain, and the domain that we're solving is the one here. You can see here on the left. So it's basically the whole Arabian Peninsula. You provide boundary conditions, you discretize the domain, and the resolution that we're using here is something around 6 kilometers. So it's very, very high resolution. And then we can basically solve the equations, the Navier-Stokes equations, which is basically saying I'm enforcing the law of physics in the atmosphere for all this domain, and you can come up basically with the velocity field, which of course is the wind speed field. The other nice part of this code is that since we are solving the RANS equation, so Reynolds averaged, and by that I mean that we are actually explicitly resolving the mean flow, but we are parameterizing the turbulence. And by doing that, we actually can have a very fine vertical spacing. So on the horizontal direction, we have grid cells that are 6 kilometers large, but at the same time, we can have very, very fine vertical spacing, like 20 meters in the vertical dimension, which allows us to basically reconstruct the vertical profile of wind speed, which is also very, very important. for example, to understand how tall should be a turbine, because of course different regions would experience different wind vertical profiles, and therefore like the choice of the height of the turbine, of the hub height, is very much dependent on this. We also ran some microscale simulations, and I'm going to talk about at the end of the presentation, since this is kind of the future development that we are now going through. So if you actually translate the modeling framework that I was showing before, so this modeling framework here, from words to math, what you end up with is an optimization problem. So what we want to do at the end of the day is to minimize the so-called LCOE, so the levelized cost of energy, which is saying the amount of money that you have to pay through the lifetime of the project per unit of energy that you're producing. So you want, of course, to minimize the amount of money that you have to pay per the same amount of energy, given some decision variables. And the decision variables in which we can act upon are the height of the turbine, that H, the model of the turbine. So there are different manufacturers with different, very different wind turbines characteristics. So we can choose upon this model M, and then we can choose where to build the turbines and which grid cell K, right? So we have these three decision variables. Actually, K is a vector, as well as, H and 2. So we have this decision variable space, which is H and K, and we have to minimize a function, which is the LCOE. So basically, once you select a certain H, a certain M, and a certain K, we can calculate what would be the LCOE based on the wind data that we have calculated with our simulations, based on the power curve of different model of the turbine, based, of course, on where you are in the map. And this is an optimization problem, and it's actually a constrained one, because we need to, first of all, satisfy a certain capacity that we want to install. So this phi that you see there, the big phi, in our case would be 16 gigawatts. And of course, there are a discrete number of manufacturers, so M should be limited in a big, in a set that I'm calling big M, as well as H is limited in a set that is called big H. So those are the constraints of our optimization problem. Bottom line is, if you solve this optimization problem, and you can do it after you ran your wind speed simulations at very high resolution, as I was mentioning before, you can end up with a map like this, right? So the one you see in the middle here is basically say, for each grid cell, what is the best combination of model, turbine model, and hub height that basically minimizes the LCOE. For example, if you see blue in this map, it means that this Nordex N131 3.3 megawatt, that is the best or the most cost-efficient turbine for all the grid cells in which you see blue. And actually, different shades of blue represent different heights. So there are some regions in Saudi Arabia in which it's probably more convenient to go for a smaller turbine. Some other regions in which the wind speed is increasing much more if you go higher in the atmosphere, and therefore it's nicer, or it's more cost efficient to exploit the height of the turbine, and so go build taller turbines. Hopefully this makes sense so far. And at this point, you can, once you've calculated this, so for each grid cell, you have a best or most cost efficient turbine, and then associated LCOE with it, right? So at the end of the day, what we can calculate is also where. And here I'm reporting with this turbine sign symbol, basically what would be the best locations in Saudi Arabia based on our analysis. So we were given 16 gigawatts to be installed, and we calculated, and this is actually an easy calculation, that we need pretty much 75 wind farms across Saudi Arabia to satisfy that capacity. We don't need, of course, a wind speed simulation for saying that. And each wind farm would have something around 80 turbines or something like that. Once we've calculated this, since now we have all the data, because we have the wind speed data, we have the cost data, we can actually calculate much more things, like what is the total annual energy production? And it turns out it will be something around 75 terawatt hour per year, which is 26% of the total Saudi Arabia demand. So that gives you the idea on how big the investment of 16 gigawatts of wind speed would be. Because now we have all the capacity factors, and we have all this this nice data they would like to have, right? The total area covered would be something around 0.12% of total Saudi Arabia surface. So Saudi Arabia is a pretty big country. So, I mean, it makes sense that the total area covered by the wind farms, it's still a small number. Again, this modeling framework, I mean, we've developed this whole thing for Saudi Arabia, but as was mentioned before, we could actually use the same thing for other emerging countries, because we basically provided some rules on how to identify which causes should identify, how to identify certain geographical areas that are not suitable, and so they should be excluded for our analysis, how to do these simulations, or which vertical spacing you should use, and so on and so on. So in this sense, this modeling framework can be applied also in other contexts. So thanks for listening. And I've just left here the link to our research lab website, in which you can find all the publications related to this talk, as well as my contact there. If you want to discuss anything about what I've presented, of course, in 15 minutes, it's hard to go into the details. So I'm always happy to discuss more. Hopefully at the conference, we will be able to have some sort of discussion going. So again, thank you very much.